Welcome back. Next up, we have Richard Graham again, and he's going to talk about storage signature offloads.
As Bill said, I'm going to talk about some extensions that we've added in our some capabilities that have been added to our hardware to help with protecting storage data, and the Verbs extensions that have been developed to expose this capability. So a bit about the what we're trying the feature that we're trying to support. Specifically, as I said, this is aimed at helping with at offloading some of the operations that are offloading to the NIC some of the operations that are done in the context of SCSI storage, and specifically dealing with the data integrity field or the diff. So T10 diff and T10 DICs actually are the sort of capabilities that we're supporting here. I should say the support in hardware is broader for this. It supports more than just T10, but all we've exposed at the hardware level at this stage is the is T10 diff and DICs. So a bit about diff. So what diff does to storage or to block storage is it extends the block storage by 8 bytes, adding some data protection capabilities, CRC specifically. This capability was proposed about 10 years ago or so, in the context specifically of storage to disk, and then protections later on were added. The DICs capabilities were extended to protect things also in main memory. And this was brought about to help protect against some potential data corruption errors that could happen that weren't being protected up till that point. So, memory buses are protected, I/O buses are, and the like. You can read the list of things that are protected there. The list of some of the data protections. But what was really missing is support for delivering the wrong data to the wrong location, doing RAID checks on some of the wrong data, or simply trying to write along the wrong data. And so from what diff actually is, what the diff support actually is, as I said, it adds to the data sectors an 8-byte field that's used for protection. Typically, the data sectors are 512 bytes in size, but I guess now 4,096 bytes is becoming more and more popular. And so the signature has a guard tag associated with it. It's 16 bits or 2 bytes. That uses a CRC, 16-bit CRC, regardless of the size of the actual data sector, whether it be 512 bytes or some multiple of 512 bytes. It also includes a 4-byte reference tag. What's in that reference tag really depends on what sort of protection you're using. If you're using type 1, type 2, type 0 for that matter. These are the 32 lower bit, 32 bits of the sector number usually, if I remember correctly. And you can see there's a wraparound every 2 terabytes. So that's this reference tag there, and then there are tube tags that are really application tags that are up to the application as to what to do with them. So from a system architecture, the sort of thing, the sort of setup that's being addressed. So this support is intended to provide support both legacy initiators that don't provide T10 diff. So you have, actually I should step back, I'm sorry. You have, in terms of architecture, you talk about, first of all, initiators, which is which are will either write or read data to the target, which is a storage system. The both either initiator or target can be legacy, that is, legacy that doesn't support T10 diff, or of course they can support T-diff. Same thing on the target side of things, although this figure doesn't show it. So the data may come from memory without any sort of protection. Add protection to it, send it over the wire, and then something happens on the remote side, with the data. Data integrity checks are performed. So a few, from a read perspective, there are several possible combinations in terms of the sort of data transfers that may happen. So first of all, the data blocks are the sort of whitish colored blocks. The red are the guard blocks. So you may have data that originates from from storage that has the protection on it. It ends up in main memory without any protection. So this could be, for example, a legacy device. The data can go over the wire with the data protection that is sent as intact. And what's done at the transfer point, and this is the data is validated. That is, as the data is being sent, the guard block is being checked to make sure it matches what's on storage. And then when the data arrives at the other end, after the data is validated, before it's delivered to memory, it's stripped and delivered to memory without as contiguous data blocks, without the data protection. Similar thing for the data can go over the wire without any protection. That is, you can strip the data. The guard blocks can be stripped from before the data is sent, and so there are no checks on the other end. The data can again start with protection, transferred on the wire with protection, so it's validated at the transfer point, arrives at the other end, and so it's validated at that point too. And delivered to main memory with the guard blocks. And similarly, finally, you can also start with data that has no guard blocks, generate the guard blocks once the data arrives to the other end, and store those guard blocks in main memory with the data. On the read side, you can have the data coming from memory with or without protection, check protection. Or add the protection blocks to the data on transfer. On the right side, again, data is originating from memory. It can come with the protection blocks or without the protection blocks. The HCA can add the protection block then if it's without it as it goes out to the network and validate it on the other end. It can send it without the protection and add protection blocks as it arrives, and so in storage it will have the protection with it. It can start in main memory with data protection blocks, transfer over the wire with data protection blocks, and be stored with the protection blocks, or the data can be stripped in the process. So these are the sort of operations that are supported. From a Verbs API perspective, the extension to support this involved basically extending four functions in the verb interface. One is adding a new verb to create memory protection regions that also allows that lets you describe the particular memory key as providing signature support. This relies on another feature that I'll describe soon here called user managed memory registration, which allows you to create memory keys in user space. And that was the reason, which is the reason this new verb for creating memory, new memory regions or new memory keys was created. When setting up the QP, a new attribute needs to be added to the QP to indicate that the QP will support data integrity checks. When actually wanting to do memory protection operations, there's a need to register a new memory key that describes the sort of operations that will be done. This is user level. It's done through a send operation. It's a local operation, very fast. On our HCAs, for example, if I remember correctly, latency is around 0.3 of a microsecond or so to set this up. You provide the data, a memory key describing the data that's going to be transferred, the type of protection capabilities that will be provided. That is, it describes the protection buffers, the attributes for the signature, and basically enables results in a signature enabled memory key, which then can be used in any operation for any of the operations that use memory keys. So send, receive, RDMA write, RDMA read, and the like. Once the operation is complete, there's a check. You do a check to see if there was an error or not. So there's a fourth verb added for that check. So as I said, this feature relies on an additional feature that's supported in our HCAs, and that's the ability of hardware to deal with non-contiguous memory beyond just the SGE lists that people that are defined in the Verbs interface today. So there are two types, and this feature is called the user mode memory registration. This is fast registration, and that's intended to happen actually in the critical data path. And so what's done in these memory operations, there are two types of memory registrations, two types of memory keys that are supported. There are memory keys that basically let you take pre-existing, pre-registered memory regions and take portions out of each of those regions and create a new virtual address region, a new contiguous virtual address region. No alignment restrictions exist whatsoever on the data, and I have a cartoon here that will describe this a bit better in just a moment. It also supports, in a very compact way, regular data representations. That is, data that can be represented as some base pointer, a size of an element that you're going to send, a stride between the elements, and the number of elements that you're going to send. So you have the ability to create to take regions of non-contiguous regions of memory and define a memory key that describes that region. And what this gives you is it gives you the ability, any place you can use a memory key, you can now the hardware will handle the non-contiguous data transfer without any need to do something special, anything on the software side of things. And specifically what this enables you to do, aside from things like helping with the T10 diff support, is do an RDMA operation from non-contiguous memory to non-contiguous memory without software involvement. And so from a cartoon perspective, as I said, there are two types of regions of memory that are supported. One is where you take previously defined memory regions. So what this doesn't let you do, this doesn't let you arbitrarily map regions of memory. You still have to go through the kernel to create the initial memory protections on these regions. So it lets you take memory from an arbitrary number of regions with no alignment constraints whatsoever, and create a memory key that describes these regions as a contiguous region of memory. So, for example, a thing that this can help you with is if you're using some sort of algorithm where you need to gather data, rather than data that specifically may not be aligned, or data that may have more than the limit that you have on the limit that's supported on the length of your SGE list. you can basically create this new memory region, and instead of having to copy the data into some sort of contiguous region before you send it, or on the receive side, instead of having to, if you're doing an RDMA put, for example, or RDMA write, I'm sorry, instead of getting the region contiguously on the other side and then scattering it by software or something like that, you can simply go non-contiguous to non-contiguous. Also, as I said, this feature supports taking regions that are non-contiguous in memory, but have a regular structure to them in one dimension. So if memory is contiguous from left to right, up, down, you can take every nth element, and you could create a virtually contiguous memory key that describes this as a virtually contiguous region. You could interleave two or more of these regions and describe them, and put a region that basically provides the interleaving. And so again, this happens without having to do any memory copies or anything like this. So this feature in particular can be very useful for things like T10diff. Not to mention some of the things like MPIs or the like, any sort of data transfer where you're using more than just simple data types and the like. So you can use this, for example, to describe structs. And all this is handled by the hardware. You can also do the reverse. You can take data that's interleaved and split it. Describe a memory key that's split it. And again, any place a memory key can be used, you can use these memory keys. So getting back, so again, the support for T10diff really does rely on this capability. It relies on the abilities to gather and scatter of data, to be able to pull protection data from a different location in memory, for example, relative to the block of data that's going to be written to the storage to the target. And so when it comes to sort of what one does, for example, in a SCSI transport using these capabilities, I have two flows here. One is when data is being written from the initiator to the target. So on the initiator side, there are things that are set up before the data is transferred. So you'll set up the memory keys, you'll set up the description of memory and the like. You'll also do whatever protocol is necessary, for SCSI. Send that information. Post the work request to generate the memory key that describes the memory region to which the data is going to be read into. From the target, send the memory key to the target. The target sets up its own memory keys for the data transfer. Does an RDMA write. Checks to make sure that on the outcome of the signature operation, whether it passed, whether data was transferred on this side intact or not. Lets the remote side, the remote SCSI initiator know what happened, and the initiator on its side checks to see the outcome of the signature operation on the data that was received. So there's signature operations on both sides. Same thing on the SCSI write. Again, set up the memory keys for the memory protection. Send the information to the Send the information to the target. The target sets up its memory keys for receiving the data. Does a get on the data? Checks the outcome of the data to see whether or not it passed. The data was transferred correctly. Sends a response to the initiator. The initiator checks on its side to see if the data that it delivered went out on the wire. Okay. And then you're done. There's some memory and validation on the keys here again to make sure that keys are used only when they're validated. And that is the the description of this feature. So any questions? Yes?
Enabling the signature, shouldn't it be part of the modified software? Because once you negotiate the connection with the other side and if you know that it supports that it and there, then when you change the state to RTR, you can set that property.
Actually, we don't have to. There doesn't have to be a negotiation. The other side doesn't have to support it. If you look, so what happens if the other side doesn't support it? Then the way the system is configured, you would strip. You would either, depending if data if data is originating or ending at the particular QP, you would either strip off the signature as it's going out, or you would append it as it's coming in. You know, calculate it as on the data that's coming in and append it. So there's no need for the negotiation that happens at a level above verbs at the SCSI layer in terms of setting up the correct characteristics for the Q pairs. Yes?
Is this feature a hardware feature or the software feature?
Hardware. It's a hardware feature, yes.
Is this only was on the receive side?
No, it's both sides, both on incoming and outgoing, and it can be configured as to what you do on each side. And that's what setting up the signature M key does, is you're actually configuring the properties that you want for the particular operation. You're doing it on a case by case basis. Okay. Any other questions, or if not, this is it. Okay. Thank you.